Hello students, so we start a new topic, that is electrochemical cell and gives free energy. Now we mostly get numerical from this topic, but you have to know how the gives free energy decides the nature of reaction. Gives free energy is represented by delta Z or delta Z naught. Delta G is at a given concentration. Now for a reaction, if you change the concentration, if the concentration is not equal to 1, then the gives free energy is delta G. But if the concentration is 1, it's known as standard gives free energy and is given by delta Z naught. If delta G or delta Z naught, if it is positive, the reaction is non-spontaneous. That means the reaction will not take place by itself. If it is negative, the reaction is spontaneous. It will take place by itself. And if it is 0, then the reaction is in equilibrium. So in question, if you are asked to find out whether the reaction is spontaneous, non-spontaneous, or in equilibrium. So what do? You calculate the value of delta Z or delta Z naught, find out if it is positive, negative, or 0. If delta Z is positive, the reaction is non-spontaneous. If it is negative, it's spontaneous. And if it is 0, the reaction is in equilibrium. So the formula to relate gives free energy with electrochemical cell is delta G. Delta G equal to minus NF E cell. And delta Z naught is equal to minus NF E naught cell. Now you can see here, if you are going to calculate the gives free energy at a given concentration, you use the electrode potential at a given concentration. If you are going to calculate gives free energy, that is standard gives free energy, then you will use the standard electrode potential. So let us take a question from this topic. The standard electrode potential E naught for Daniell cell is 1.1 volt. Calculate the delta Z naught for the reaction. So the reaction given to us is Zn as plus Cu2 positive aqueous gives Zn2 positive aqueous plus Cus. So you can see from the question, the standard electrode potential, that is E naught, is given. We have to calculate delta Z naught, that is standard gives free energy. So first, you write on the formula, that is delta Z naught is equal to minus NF E naught cell, where N is the number of electrons. So if you see the reaction, the number of electron transfer which is taking place is equal to 2. So N equal to 2. F is Faraday's constant. You know the value, 96500 coulomb per mole. E naught cell value is given, is equal to plus 1.1 volt. So let us put these values here and simplify. So minus 2 multiplied by 96500 multiplied by 1.1. Unit is joule per mole. So if you simplify this, you will get 212300 joule per mole. Or we can write minus 212.3 kilojoule per mole. Now in case if you are asked, find out whether the reaction is spontaneous or non-spontaneous, you can see it's negative, so the reaction is spontaneous. So the the next topic which we are going to start is conductance of electrolytic solution. So when it comes to electrolytic solution, when we calculate conductance, there are few terms which you need to know. Resistance, specific resistance is also known as resistivity, conductance, conductivity. Conductivity is also known as specific conductance. Molar conductivity. So to start with resistance. So we know resistance is an obstacle to the flow of electric current. So if the electric current is trying to flow, the resistance is a property which will obstruct it. So if we take a conductor having length L, small letter L, an area of cross section A, resistance is directly proportional to L and is inversely proportional to A. So if you combine, resistance is proportional to L by A, or R is equal to rho L by A, where rho is constant and is known as resistivity or specific resistance. Resistivity. L is length of conductor, A is area of cross section, so L by A is known as cell constant. Next, let us see how to define resistivity or specific resistance. So we have R equal to rho L by A. So if you consider a conductor of length L, area of cross section A, resistance is equal to rho L by A. So if length of conductor is 1 centimeter, area of cross section is 1 centimeter square, then resistance is equal to rho, that is resistivity. So from here, resistivity or specific resistance is defined as the resistance when the length of the conductor and area of cross section is unity. For resistance, the unit of R is Ohm, or you can use the symbol. For specific resistance, rho, the unit is written as R. Rho is equal to R A by L. So rho resistance is Ohm, A is centimeter square, L is centimeter, so Ohm centimeter. So unit of specific resistance or resistivity is Ohm centimeter. Next is conductance. Conductance is defined as the reciprocal of resistance. So G is equal to 1 by R. Unit of G is equal to Ohm inverse, or you can write MHO, mho, or you can use the symbol Ohm inverse. Next is conductivity or specific conductance. It is given by kappa, and conductivity or specific conductance is defined as the reciprocal of specific resistance or resistivity. So 1 by unit of kappa is equal to 1 by ohm centimeter. So we can write ohm inverse, centimeter inverse. Ohm inverse is written as Siemens, that is S. So Siemens per centimeter. This is the unit of conductivity. Next is molar conductivity. Molar conductivity is defined as the conducting power of all the ions produced by dissolving 1 mole of an electrolyte. Say you take a solvent, and in the solvent you dissolve 1 mole of an electrolyte. So the conducting power of the 1 mole of an electrolyte in the solution is known as molar conductivity, and is given as kappa, that is conductivity, multiplied by 1000 divided by molar concentration, that is Cm. Unit of molar conductivity is equal to Siemens per centimeter square per mole. Next, let us take a numerical from this topic. The resistance of a conductivity cell when filled with 0.05 molar solution of an electrolyte X is 100 ohm at 40 degrees centigrade. The same conductivity cell filled with 0.01 molar solution of electrolyte Y has resistance 50 ohm. The conductivity of 0.05 molar solution of electrolyte X is 1.0 multiplied by 10 to the power minus 4 Siemens per centimeter. Calculate number A, cell constant, number B, conductivity of 0.01 molar Y solution, and number C, molar conductivity of 0.01 molar Y solution. So you have to find the cell constant. Cell constant is L by A. Now since there are two different concentrations, 0.05 molar and 0.01 molar, and is given for both the concentration of solution, we use the same conductivity cell. That means the cell constant will remain same for both 0.01 and 0.05. So let us use the formula R equal to rho L by A. So we'll find this, R is given. Now instead of rho, that is specific resistance, we'll use kappa, that is conductivity. Now why conductivity? Because the specific resistance is not given for 0.05, but instead we have the conductivity, that is kappa. So from here, cell constant L by A is equal to resistance multiplied by conductivity. Resistance for 0.05 molar solution is given and is equal to 100 ohm. So 100 multiplied by conductivity is 1.0 multiplied by 10 to the power minus 4. So if you simplify this, this is equal to 10 to the power minus 2. Unit is centimeter inverse. So this is the cell constant. Next, we have to find the conductivity, that is kappa. So we use the same formula, R equal to 1 by kappa multiplied by L by A, cell constant. Now, since we are using the same cell, the cell constant will be same. So we'll use the same L by A value here. We'll put the value of resistance and we'll find out conductivity. So from here we can write conductivity is equal to 1 by R multiplied by L by A. So it's given the resistance is equal to 50 ohm. So 1 by 50 multiplied by cell constant is 10 to the power minus 2. So if you simplify this, you'll get the answer. Next, molar conductivity is equal to kappa, that's conductivity multiplied by 1000 divided by Cm. So if you put the value of conductivity from here, molar concentration is 0.01. You simplify, you will get the value of molar conductivity. So I want you to try this by yourself. So that's all from this chapter. In the next video, we'll start a new chapter. Thank you.